So far, we have learned two ways of regularization in the deep learning models. First is dropout, which is turning off some random neurons in the network, and we drive that subnetwork, the produced subnetwork, to be sufficient to produce good predictions. The second way is the early stopping, which is basically stopping the training at a specific point when there is no improvement for a specific number of epochs, which we call patients. We made this before the models start to overfit the training set. The third way that we will study is the data augmentation. One of the ways to reduce the variance and reduce the overfitting of the deep learning model or any learning model is to increase the number of data set. But it's not always applicable in all problems, and it's not always possible in all cases, as it's sometimes very hard to collect more data set. Here, data augmentation comes with the solution. Theoretically, we will increase the number of data, like the amount of data set, by making some random transformations to the original set. But these random transformations for any image will not change its output, it will not change its class. So for example, if you are like making some classification model to cats and dogs, the image of a cat will still be a cat after the transformation. This basically will make the model more robust to changes, and it will make better generalization, it will make better testing accuracy, and it will reduce the overfit and the variance of the model. So let's see some examples of this transformation that we can do to the training set that we have. First is a random flipping that we can do to the images, either horizontal flipping or vertical flipping. And this is the original set. Take care that these transformations, when you choose them, it should be appropriate for the problem that you are having now. Some transformation, for example, if you are classifying the images of digits from 0 to 9 to some to the classes, which is the digit class. When you, for example, if you flipped the image of 6 horizontally and vertically, it will be 9. And this is not appropriate, and it will change the class of the image. And it will make a problem in the classification and the training. And the model should be confused between the images after the transformation. Second example, for example, is the rotation. When you rotate some image, it will still be the same cat. Here we transform, like we rotated by 22.5 degree, and here minus 22.5 degree. Same image, same cute cat, same label. What others like transformation you can do? Random cropping for the image. And after cropping, the image is resized, whitening, center the input mean to 0, or even like standard normalization. Random affine transformation, read about affine transformation in the internet. And bright shifting, like random width and height shifting. We've also random zooming for the image, either zoom out or zoom in, and more. Let's see how we can do this in class. First, we need to import this generator from class that we will use to generate the new images or make this data augmentation. Class dot preprocessing dot image import image data generator. So let's make a class of this. Let's make an object from this class generator. Here in the parameters, we will define the transformations that we want to do. For example, like feature-wise center, sample-wise center, feature-wise standard normalization, and so on. What I will choose here for this problem first is a rotation. Rotation range is, it can be a tuple, for example, like from, I want the degrees to shift, to rotate the image from -10 to 10 to 15, for example. But if we provide it like only float, it will make the range itself. For example, here I provided 20, so the range will be from -20 to 20. And I feel this is appropriate here. And with shift range. With shift range is like basically some fraction of the whole weight. And yeah, it's a fraction of the whole weight that we want to shift the image for horizontally. So randomly shift the image horizontally, and this fraction from the total weight. So for example, if I choose it 0.1, it chooses only like p from 0 to 1. So like we will shift the image horizontally by from 0 to 10% horizontally. Same for the height. I'll choose also 10%. So the image will be shifted randomly from by some like value from 0 to 10%, either up or down, and also either right or left in the width shift range. Other parameters that we have: shear range, which is something related to the affine transformation, and this is the shear angle. Zoom range. Zoom range also, it should be like some lower and upper bound, but if we put something like 0.15, then the range will be something like this. The range of the zooming will be from 1 minus 0.15 to 1 plus 0.15. So the image will be increased by 50%, or it will be zooming in or out by 50%. This is what when you provide the zoom range as a float. What else? Oh, we can choose, yeah, horizontal flipping also. It's very nice for this problem. Of the true, so it's like 50% the image, by 50% chance, the image will be flipped horizontally. I will not choose vertical flipping. I don't think it's appropriate here. Maybe you can try it. So what else? I think, yeah, that's it. Yeah, one important thing is the validation split. This generator also, like, what it does basically generate some patches of data that transform data. So you need to specify the validation split inside it. So I'll put also 50% as it is here. And that's it. One thing that I don't want to forget, the generator.fit. Here you pass the X-ray. What is like it is doing here, basically it collects some statistical information about the training set that some transformation here may need, especially like specifically the transformation that needs this fit function, the C8 whitening, if this is true, or feature standard normalization if this is true. If this is true or this is true, then you need to make this fit function. But as we didn't use them, we will not need this generator.fit X-ray. Here we will give him, we will like make this generator generate some batches for us on the training set. Flow, X-train, and Y train. Batch size, same as batch size here. So we don't need here batch size, as we will get the batches from all like directly from the generator. And for the validation set, it will not be a validation split because we will get the validation directly, the validation generator, same from this generator object. But I would choose don't generate the training subset, choose the validation subset that we will specify here with 15%. Generator.flow, same X-train, and Y train, size similarly, 128. Subset, validation, and that's it. One more parameter that is new here in the fit function is steps Why we need this? Here, this generator generates patches, and for each epoch from this 13 epoch, the model may not he doesn't know how many patches he should get from this generator. Should ask from generator to generate. So I'll tell him generate, so that we can loop on the whole data set. It will be the length of the X train over the patch size, which is 120. By this, we will loop almost on the whole data set. For each step, we will generate one patch, and this patch size is 128. So by this simple equation, we can loop on the whole images, transform it. That's it pretty much for the generator and for the data augmentation. Please try this. You will notice that the accuracy increased before this. Maybe it's something 72%, and after this it will be 80 or more than 80%. Maybe also you want to increase the number of epochs to notice how it will increase the accuracy.